Good day to Dr. Ali. We are from Group 6. Our team members are Anis, Effie, and me, Shin.
So first we need to analyze the two forces involved. The first one is the restoring force, which is Fs equals to negative Kx, and secondly is the retarding force, which is Fd equals to negative C dx over dt. So next we apply the Newton's second law and we substitute our expression. And then we will get the expression of m d square x over dt square equals to negative kx minus c dx over dt. So move all this term into one side and we will get our second order ordinary differential equation. So the whole equation is divided by mass to make it more simplified, and then the variables is expressed by a single alphabet. So according to the characteristic equation, we can get it as m squared plus pm plus q equals to 0. So by applying the quadratic formula, we will get m1, m2 equals to negative p plus minus square root p squared minus 4q over 2. And when we separate these two distinct values for m1 and m2, we will get our general solution formula for the displacement over time. So we can determine the suspension's behavior by looking at the discriminant p squared minus 4q. If it's greater than 0, the system is overdamped. If it's equal to 0, the system is critically damped. And lastly, if it's less than 0, the system is underdamped.
For the simulation, I used the differential equation derived in part 1. The chosen mass is 2.317 kilograms and the spring constant is 18.693 Newton per meter. The initial displacement is 0.150 meter and the initial velocity is 0. The critical damping coefficient is calculated using the formula C equals to 2 third mk, which gives 13.162 Newton second per meter. To obtain the four different behaviors, I kept the mass and spring constant fixed, but changed the damping coefficient. For the undamped case, C is equal to 0. For the underdamped case, C is smaller than the critical damping coefficient. For the critical damped case, C is equal to the critical value. For the overdamped case, C is greater than the critical value. The first graph shows undamped condition. Since there is no damping coefficient, the system keeps oscillating with constant amplitude. The second graph shows underdamped condition. In this case, the system still oscillates, but the amplitude decreases with time because the damper removes energy from the system. The critically damped graph shows that the coilover returns to equilibrium without oscillation and in the shortest time. For the overdamped case, the system also does not oscillate, but it takes a longer time to return to the equilibrium because the damping force is too large. Based on the simulation, increasing the damping coefficient reduces the oscillation of the coilover. The undamped and underdamped cases show oscillatory motion, while the critically damped and overdamped cases do not oscillate. However, if the damping is too large, the system returns to equilibrium more slowly.
On this slide, we compare the four damping conditions: undamped, underdamped, critically damped, and overdamped. Each condition has a different graph and behavior. Undamped oscillates continuously, underdamped gradually settles down, critically damped returns to equilibrium the fastest without oscillating, while overdamped also reaches equilibrium without oscillation but much more slowly. Here we explain the first conditions. In the undamped case, there is no damping force, so the system keeps vibrating with constant amplitude, making it unsuitable for vehicle suspension. On the other hand, the undamped system gradually loses energy, giving a smooth ride while maintaining good tire contact with the road. This is why it is commonly used in automobiles. This slide discusses the remaining two conditions. A critically damped system returns to equilibrium in the shortest time without overshooting, making it suitable when fast stabilization is needed. Meanwhile, an overdamped system also avoids oscillation but takes longer to return to equilibrium, which can make the suspension feel stiff and less responsive. Based on our comparison, the underdamped response is the best choice for automobile suspension. It effectively absorbs road shock, provides better passenger comfort, maintains tire contact with the road, and offers a good balance between comfort, stability, and handling. In conclusion, our project shows that a second-order differential equation can effectively model the behavior of a coilover shock absorber. Among the four damping conditions, the underdamped response is the most practical because it quickly returns to equilibrium while still allowing small oscillation. This gives passengers a comfortable ride while keeping the vehicle stable and safe on different road surfaces.